You click a link, and in what feels like an instant, a website from the other side of the planet just appears on your screen. It feels like absolute magic, right? But it's not. It's actually this incredible, complex dance of rules and protocols all working together perfectly. In this explainer, we're going to pull back that curtain. We're going to show you exactly how that magic works, from the big ideas down to the practical details.
This is the big question, the one we're diving deep into today. We're going to follow the journey of that data, step by step, to really understand the amazing choreography that happens every single time you click. The best way to think about it is like a global postal service, but one that moves at the speed of light. It's a pretty cool story, so let's get into it.
All right, so here's our roadmap. First, we'll talk about the internet's postal service to get a handle on the different layers of communication. Then we're going to zoom in on the addresses themselves. What are they, and why did the original system need such a massive upgrade? After that, we'll look at how network admins slice and dice their networks. And then, to cap it all off, we'll put our knowledge to the test with a few real-world problems. To really get our heads around how the internet works, let's start with something we all get: sending a letter. You drop a letter in a mailbox, and you don't think much about it, but you've just kicked off this whole chain of events. It gets sorted, routed, put on a truck. Well, sending data online is surprisingly similar. It's not just one thing, it's a journey through different layers, and each layer has a very specific job to do. This whole system is what we call the communication stack. At the very top, you've got the application layer. This is where you are, browsing a website or writing an email. Now, once you hit send, your data goes to the transport layer. And here, a big decision gets made. Do you need a delivery that's 100% reliable, where every single piece is accounted for? That's TCP. Think of it like certified mail with a tracking number, perfect for downloading a file. Or do you just need it to be fast? That's UDP. UDP is like sending a postcard. It's quick, but there's no guarantee. This is perfect for something like a video call, where you'd rather have a tiny glitch than have the whole stream pause to find one lost pixel. After that, the network layer acts like a GPS, finding the best route across the internet. And finally, the data link and physical layers are the actual trucks and the roads they drive on, handling the physical trip from point A to point B. So let's really focus on these two, because they're doing the heavy lifting. The network layer is the master navigator. Its only job is to look at the final destination, that IP address, and figure out the absolute best path through the entire maze of the internet. It's the GPS. The transport layer, on the other hand, is all about the quality of that journey. It doesn't care about the route, but it is obsessed with how the data gets there. Is it reliable? Is it in the right order? Or is it just fast? It's the difference between the route planner and the actual delivery service you choose. Okay, so we've got our postal service and our delivery options, but none of that means anything without the single most important piece of information: the address. Just like a letter needs a street address, every single device on the internet needs a unique identifier. And that's where the Internet Protocol, or IP, comes in. An IP address is basically the universal language of location on the internet. It's a unique number assigned to your phone, your laptop, the server you're trying to reach. Everything. Without this digital home address for both the sender and the receiver, communication just flat out wouldn't be possible. Now, in the early days, these IP addresses were grouped into classes. A Class B network, for instance, gave an organization a block of addresses that could handle up to 65,534 devices. Now, that sounds like a lot, right? But think about a big university or a company in the 90s. They could burn through that pretty fast. And the system was so rigid that it created a ton of waste, with huge chunks of addresses going unused. And this is what happened. The internet's growth wasn't just steady, it was an explosion. Suddenly, billions of devices were coming online, from servers to PCs to the first smartphones. The original system, called IPv4, just wasn't built for that scale. We were headed for a crisis. The internet was literally running out of room. So the solution was a complete do-over: IPv6. The number of addresses IPv6 offers is just mind-boggling. I mean, it's enough to give an IP address to every single atom on Earth and still have addresses left over for 100 more planets. But it wasn't just about more space. IPv6 was a chance to rebuild the internet's foundation for the modern world. It was designed from the ground up for video streaming, for mobile devices that are always on the move, and with security big right in from the start. All right, so now we have these massive blocks of addresses, but how do you actually manage them inside a big organization? You can't just have every single device on one giant, flat, open network. For security, for performance, for basic organization, you need to be able to divide it up. This is the art of subnetting. Think about a company's office. You definitely don't want the computers in the accounting department talking directly to the devices on the public guest Wi-Fi in the lobby. Subnetting lets you build those digital walls. It's like taking a big open-plan office and creating private offices and secure meeting rooms. It keeps traffic separate, boosts security, and just makes the whole thing run better.
So, how do we build these walls? It all comes down to something called a subnet mask. A subnet mask is a special number that tells a computer which part of its IP address identifies the entire network and which part identifies the specific computer. You can see here for a default class B, the first half, all the ones, that's the network part. It's the same for every device. The second half, all the zeros, that's the host part. That's what makes each device unique.
Now, this is the really cool part. Subnetting is literally the act of borrowing some of the bits from the host section and using them for a new purpose. You're effectively sliding that dividing line over. By turning some of those host bits into subnet bits, you create this new middle section, and this is what creates all your smaller subnetworks. Of course, it's a trade-off. The more bits you borrow to make more subnets, the fewer bits you have left for individual computers on each subnet. It's this balancing act that lets network admins tailor their networks perfectly. Okay, we've gone through the layers, the addresses, the whole subnetting idea. Now, let's stop talking theory and actually put it into practice. We're going to walk through a few questions from a networking assignment and see how these concepts are used to solve real problems. All right, here's our first puzzle. We have a Class B network, and we have two requirements. We need to create at least 500 different subnets, and each one needs to have room for at least 100 computers. Our job is to figure out the one subnet mask that makes both of those things happen. This is a classic networking problem. Let's walk through this. First, the subnets. We need 500. Since computers think in binary, we have to think in powers of 2. So what's 2 to the power of 8? That's 256. Not enough. Okay, let's try borrowing one more bit. What's 2 to the power of 9? 512. Perfect. That covers our 500 subnets. So we need to borrow 9 bits. Now for the hosts. A Class B address starts with 16 host bits. We just borrowed 9 of them, which leaves us with 7 bits for hosts. 2 to the power of 7 is 128. But you always have to subtract 2 addresses in any subnet, one for the network itself and one for the broadcast. So that leaves us with 126 usable addresses for computers, which is more than the 100 we need. So it works. And borrowing those 9 bits gives us our final mask, 255, 255, 255.128. Next up, a question about IPv6. I know these addresses can look pretty intimidating with all the colons and letters, but they actually follow a couple of very simple rules. Our job here is just to spot the one that's breaking the rules. Okay, here's the main rule you need to know. A full IPv6 address always has 8 groups of characters separated by colons. Always. But because that's really long, there is a shortcut. You can use a double colon, double semicolon, one time to represent a string of groups that are all zeros. So if we look at our options, D only has 4 groups, and there's no double colon to stand in for the missing 4. That means it's incomplete. It's not a valid address. The others either show all 8 groups or they use that double colon shortcut correctly. And for our last question, we're coming full circle, all the way back to the communication layers we started with. We're looking at a critical piece of networking gear, a switch. Switches connect all your devices together, but depending on which layer they operate at, they do their job in a very different way. So what's the deal with layer 2 versus layer 3? This table makes it super clear. A layer 2 switch operates at the data link layer. It sends data around using MAC addresses. A MAC address is the permanent physical hardware ID of a network card. Think of a layer 2 switch like a local mail carrier who only knows the names on the mailboxes on one specific street. A layer 3 switch, however, works at the network layer. It's much smarter. It uses the logical IP addresses we've been talking about, so it understands the entire network map. And that's the key takeaway. A layer 3 switch is just plain smarter. It's really a high-speed switch and a router combined into one device. It doesn't just ask, who's my immediate neighbor, like a layer 2 switch. It asks, what's the best path across the entire internet to get this data to its final destination? It can make those big picture routing decisions. That's something a layer 2 switch could never do. So we've gone on this whole journey through the layers, through IP addresses, subnetting, but if you had to boil it all down to just one single idea, the core function that makes the whole internet tick, what would it be? What is the network layer's most important job? And this says it all, perfectly. Everything else we talked about, all the different layers, the complex addressing, the smart hardware, it all exists to serve this one single purpose. The fundamental genius of the internet, the job of the network layer, is to look at a nearly infinite number of possible routes and find the best path for a tiny packet of data. And that, right there, is the real magic behind every single click.